Okay, so in this video we're going to talk about instantaneous rate of change. Okay, so let's start by looking at an example. So we're going to consider the average rate of change, something we've talked about before, of the function f of t equals 100 minus 16t squared for t equals 1 to t equals b, as b gets closer and closer to 1. Okay, so let's do some computation. So we're going to pick some b values. We'll start with 2. It's not very close to 1, but it's the closest integer to 1, or one of the closest integers to 1. Then we'll do b is 1.5. We'll do b is 1.1, 1.01, and then 1.001. And then we'll see if we can't see a trend here. And then what we're going to do is we're going to do the average rate of change. So the average rate of change in a position context, position versus time context, is the average velocity, v bar. It's going to be f of b minus f of 1 over b minus 1. Okay, so now we're going to do this computation for 2, b is 2, b is 1.5, b is 1.1, etc. I'll do the first calculation just to show you how this works, and then I'll just leave the computations for you to do the rest of the computations for you to do on your own, and I'll just tell you the outputs. So if we put 2 into this, the output at 2 is 36, and the output at 1 is 84. And that's negative 48 over 1, so we get negative 48 feet per second. So this first entry in the bottom row is negative 48. And so I'll just tell you what the other ones are. We get negative 40, we get negative 33.6, we get negative 32.16, and then we get negative 32.016. So it appears that as b gets closer to 1, that our velocity gets closer and closer to negative 32 feet per second. Okay, so now I want to reframe this table in a slightly different way. I want to introduce a new variable. We'll call it h. And h is going to be the difference between b and 1. If h is the difference between b and 1, then b is going to be 1 plus h. So I want to take this first row of the table and rewrite it in terms of h. So h is 1 less than all the b entries. So it's going to be 1, 0.5, 0.1, 0.01, and 0.001. And then the average velocity, if we write it in terms of h, is going to be f of 1 plus h minus f of 1 all over h. And its outputs are going to be the same numbers. It's still the average velocity. It's still going to have these same outputs. We're just thinking about it in terms of h. So again, we see that the average velocity seems to be approaching 32 feet per second. But instead of b going to 1, we have this h going to 0. So as h goes to 0, we're hypothesizing that v goes to 1. This average velocity goes to 1. A little more formally, our hypothesis is the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h equals negative 32. Okay, and this form naturally leads to what we call the derivative. So let me define the derivative. So the derivative of a function, typically our functions a function of x. In the example we've been looking at, it's a function of t. At a point x equals a is the limit as h goes to 0 of f of a plus h minus f of a all over h. And it's called, this derivative is called f prime of a. It's also called the instantaneous rate of change of f of x at a. So what is the derivative graphically? So the average rate of change, you'll recall, is the slope of the secant line through 2 points. So if we have a and then we have some a plus h where h is not 0, excuse me, we're going to have these corresponding outputs, f of a and f of a plus h. And the average rate of change is the slope of this line. If, however, we take the limit as h goes to 0, what we're doing is we're taking this right endpoint and we're sliding it along the curve closer and closer. And as we're doing that, we're getting the slope of this line, which is only touching the curve at one point. This is called the tangent line. So the slope of the tangent line is what this derivative is computing. Okay, so now we're ready to test our hypothesis. Now we're ready to compute this limit. And we'll call this example 2. So let's find the derivative at 1 given this function f of t is 100 minus 16 t squared. Okay, and the derivative at 1 is, by the definition we just gave, the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. All right, so we're going to put in our 1 plus h into our function. We're going to put 1 into our function, and we're going to divide by h. Okay, if we put 1 plus h into our function, we'll get 100 minus 16 times 1 plus 2h plus h squared, expanding that binomial squared. And then we're going to subtract, this is 84. We've seen this in the calculations above. It's 84. 100 minus 16 is 84. All right, continuing down with the algebra, we're going to have 100 minus 16 minus 32h minus 16h squared. And you can see 100 minus 16 minus 84, that's going to be 0. So these are all going to cancel. And we're left with negative 32h minus 16h squared over h. There's an h in both terms in the numerator, so we'll just factor that h out and then divide by the h. And as h goes to 0, we're left with negative 32. And the units here are feet per second. So it did do what we thought it would do. The average velocity approached this negative 32 as the right endpoint, the b, approached 1. And this is sometimes called the instantaneous velocity. Instantaneous velocity. All right, let's consider what we just did graphically. Okay, we have this 100 minus 16t squared. It looks like this. We're looking at the point 1. And what we just did is we computed the slope of this tangent line at the point t equals 1. Okay, and more generally, the derivative at a point A, namely f prime of a is the slope of the tangent line at a. Okay,